Hello students, so in this video we are going to solve few MCQs right of your textbook which are most likely to be asked in your board exam. See, the MCQs which are being asked in your board exams are mostly 99% they are from the textbook, right? Few examples, few exercise sums which are very small, they are being converted into MCQs and they are being asked in the board exam. So chapter wise we will solve the MCQs which are likely to be asked in the board exam. Okay, so we'll start with chapter number 1, electric charge and electric field. So this is your first MCQ. How many? See the first MCQ. How many electrons are there in a charge of -1 coulomb? Of course, the question is from textbook only. So you have to find the number of electrons which are present in a charge of -1 coulomb. Fine, we'll use quantization of charge, which is Q is equals to NE. Q is -1 and this is what we have to find out. Charge of electron -1.6 into 10 raised to -19. So N will be equals to 1 upon 1.6 into 10 raised to -19. Right, so this will be 6 into 10 raised to 18, nearly 0.6 into 10 raised to 19 or 6 into 10 raised to 18. So your answer is option number C. Okay, so the next MCQ. Okay, see the second one is theoretical. Which device did Coulomb used for measuring force between two charged particles? Right, to measure the force between two charged particles, which device did Coulomb used? Coulomb used torsion balance. He used torsion balance. These are the options: torsion, spectrometer, spring balance or electroscope. So your answer will be torsion. Again, this is a line given in your textbook. Fine. Okay, let us solve another question. Okay, see the third one. An electric dipole is placed at an angle theta in a non-uniform electric field. Make it clear. It is placed in a non-uniform electric field. What is the net force and torque acting on the dipole? Okay. See, if the dipole is placed in a non-uniform electric field at an angle theta, right? This will be your non-uniform electric field. Suppose I am placing the dipole this way, -q plus q. Of course, when dipole is placed in a non-uniform electric field, it will experience both force and torque if it is placed at an angle theta, right? See, force will be P dE by dx cos theta. This will be the force which will be acting on a dipole, due to which it will be performing translational motion. And along with this, since dipole is placed at an angle theta, so torque will also be non-zero, right? So if a dipole is placed at an angle theta with respect to non-uniform electric field, then dipole will experience both force as well as torque, right? But if it is placed in a uniform electric field, then net force will be 0. Torque may or may not be 0. It depends on the angle. If dipole is placed parallel to uniform electric field, I am talking about uniform now, right? If a dipole is placed in a uniform electric field and parallel to electric field, then both torque and force will be 0, right? But whenever in the question, if they are asking uniform electric field, the net force will always be 0. Torque may or may not be 0. But in our question, they have said that it is placed in a non-uniform electric field. So when a dipole is placed in a non-uniform electric field, force and torque both will not be equals to 0, since it is placed at an angle theta. Clear? Clear? Okay, next one. See the fourth one. Electric field due to a uniformly charged infinite plane sheet varies with distance as. The whole chapter, this is the only case where electric field is independent of distance. Electric field is independent of distance, because for a uniformly charged infinite plane sheet, right, electric field was given by sigma by 2 epsilon naught, right? So this is the case where electric field is independent of distance. It does not depend on distance. So this is your answer. Okay. Fine. The next one. Okay, the fifth one. An electric dipole with dipole moment 4 into 10 raised to -9 coulomb meter. Dipole with dipole moment 4 into 10 raised to -9 coulomb meter is aligned at 30 degree with the direction of uniform electric field. Okay, so theta is given as 30 degree and electric field is having the value 5 into 10 raised to 4. Calculate the magnitude of torque. This is the unsolved question of your textbook exercise. So dipole is placed at an angle of 30 degree. This is how the dipole is placed, minus q plus q. This is electric field. This theta, which is given as 30. You have to calculate the magnitude of torque. Fine. So magnitude of torque is Pe sin theta. P cross E. Torque is equals to P cross E. So it will be Pe sin theta. P 4 into 10 raised to minus 9. Electric field is 5 into 10 raised to 4 sin 30, 1 by 2. 10 into minus 9 plus 4 minus 5. So this will be 10 raised to minus 4 Newton meter. Right? So A is your answer. Clear? Okay, the next one. Okay, the next one, an infinite line charges produces a field of 9 into 10 raised to 4 at a distance of 2 centimeter. Again, this is your unsolved question of your exercise. Infinite charges, line charges produces an electric field of 9 into 10 raised to 4 at a distance of 2. Okay, 2 centimeters. So that is 2 into 10 raised to minus 2 meter. Find linear charge density. Linear charge density, that is lambda. Okay, so for an infinitely long charge wire, electric field is lambda by 2 pi epsilon naught r. Right? So lambda will be E into 2 pi epsilon naught r. Just substitute the value. Electric field is 9 into 10 raised to 4, 2 into 3.14 epsilon naught, which is 8.85, 4 into 10 raised to minus 12 into 2 into 10 raised to minus 2. So lambda will be, solve this, you will get the answer 10 raised to minus 7 coulomb per meter. Okay? Clear? Fine, we will solve the other question. Okay, so the seventh one, electric field inside a conducting sphere. First of all, make it clear, conducting sphere means spherical shell. Okay, as long as electric field is concerned, if you have been told to calculate electric field for a conducting sphere, so you need to calculate the electric field for a conducting shell. Okay, so we had seen in the third application of Gauss law that charges will always reside on the surface of a conducting sphere or a shell. Now in the question you are being told to calculate electric field inside a conducting sphere, right? Inside a conducting sphere. Let us take this as a Gaussian surface. We want to calculate electric field at this point P, which is at a distance r, right? Using Gauss theorem, for r less than r, E dot dA is equals to Q by sigma Q by epsilon naught, right? But there is no charge enclosed inside this Gaussian surface. That means Q is equals to 0. So finally E dot dA will be equals to 0. Now area cannot be 0. So electric field will be 0, right? So inside a conducting sphere or a spherical shell, electric field will be 0. C is your option. Clear? Okay, the next one. Okay, the eighth one, electric field due to electric dipole at far away distance falls off as, okay, so for a dipole at far away distance means we'll take r greater than A. Okay, right? So electric field for a dipole along the axis was 2 kp by z cube. This was the formula to calculate electric field because of dipole along the axis, and along the equator minus kp by y cube p caret. So in both the formulas, electric field is inversely proportional to q, right? Cube of the distance. Z and y represents the distances. So electric field is inversely proportional to cube of the distance at far away distance, right? So this will be your option. Clear? Clear? Far away distance, it means the point where you need to calculate electric field is quite greater than the distance A. Okay, fine. The next one. Okay, the ninth one. Find the force between two small charged spheres having charges of 2 into 10 raised to minus 7 and 3 into 10 raised to minus 7 placed 30 centimeter apart. Well, this can be asked as MCQ, but this is your unsolved question given in the exercise. Okay, so there are two charges. Let us say Q1 is 2 into 10 raised to minus 7, Q2 is 3 into 10 raised to minus 7, and the separation between them is 0.3 meter, 30 centimeter, that means 0.3 meter. Okay, so now we need to calculate the forces. Both the charges are placed in air. We can use Coulomb's law. F is equals to K Q1 Q2 by R square. What is the value of K? 9 into 10 raised to 9, 2 into 10 raised to minus 7, 3 into 10 raised to minus 7 upon, what is the distance? 0.3 meter, right? 0.3, that means it will be 9 into 0.3 square, 0.09, so that will be 9 into 10 raised to minus 2, right? This get cancelled. 6 into 2, 10 raised to 7, 10 raised to 2, 10 raised to minus 5, raised to 6 into 10 raised to minus 3 Newton, right? And since both the charges are positive, so the force will be repulsive in nature, right? So this is your option. Clear? Okay, next one. So 10th one, point charge of 2 microcoulomb is at the center of a cubic Gaussian surface 9 centimeter on the edge. Okay, so what is the charge enclosed? 2 microcoulomb, right? What is the net flux passing through the surface? Actually, when charge is enclosed in a surface, flux does not depend on the area, right? So simply flux passing through the surface will be Q by epsilon naught. So this is 2 into 10 raised to minus 6 upon 8.854 into 10 raised to minus 12. So all this you will get 2.2 into 10 raised to 5. What is the unit of flux? Flux is E dot A. E means Newton upon Coulomb. A, that means meter square. So Newton meter square by Coulomb. So this is your option. Clear? Clear? The next one. Okay, this one is simple. 1 coulomb is equals to dash ESU. Well, ESU is the CGS unit of charge. ESU stands for electrostatic unit. Electrostatic unit. You can also say as state coulomb. Or in fact, Franklin, state coulomb, ESU, these are all the smallest unit of charge or CGS unit of charge. So this is the relation between coulomb and ESU. 1 coulomb is 3 into 10 raised to 9 ESU or state coulomb or Franklin, anything, right? So this is the relation between SI and CGS unit of charge. So this is your answer. Okay, the next one. Okay, what is the net force, resultant force? Net force means resultant force acting on a dipole placed in a uniform electric field. Okay, so when a dipole is placed in a uniform electric field, let us say this is uniform electric field. So it will be from plus to minus. You are placing a dipole like this. This is a dipole, minus Q plus Q. Fine. So positive charge will experience a force in the direction of electric field, right? So force on positive charge will be Q into E, right? Okay, force on negative charge, it will experience a force in a direction opposite. So force on negative charge will be minus Q into E. So net force on a dipole will be the sum of the force acting on positive and negative charges plus Q plus minus Q, that is QE minus QE, that is 0. Of course, if dipole is placed in non-uniform electric field, it will experience force. But when a dipole is placed in a uniform electric field, the net force acting on the dipole will be 0. Torque may or may not be 0, it depends on the position of the dipole. Clear? Fine. So now in the next video, we'll solve the MCQs of the second chapter, that is electrostatic potential and capacitance.